Welcome to the intersection of technology, cybersecurity, and society. Welcome to ITSP Magazine. You're listening to a new episode of Stories from Space podcast, where your host, Matthe Williams, examines the history of human spaceflight, the breakthroughs that revolutionized our understanding of the universe and our place in it, and the brave individuals who work tirelessly to advance the frontiers of our understanding. Knowledge is power, now more than ever.
The authors acknowledge that this podcast was recorded on the traditional, unceded lands of the Lekwungen peoples. Hello, and welcome back to Stories from Space. I'm your host, Matt Williams, and today I want to get into the subject of the dark universe. One of the greatest cosmological mysteries today has to do with the existence of matter and energy that we can't see, at least not directly, but which is essential if our current cosmological models are in fact correct. I am referring, of course, to dark matter and dark energy. Together, these two mysterious forces make up 95% of the matter-energy density of our universe. And yet, any direct evidence of their existence eludes us. So how do we know, quote-unquote, that they are there, that these things exist? And how exactly did we come to theorize their existence in the first place? Well, that's a rather long story, and it begins around the early 20th century with a noted scientist who would revolutionize our understanding of the laws of physics and the universe, named Albert Einstein. Now, in 1916, Einstein had just put the finishing touches on his theory of general relativity. And this was a continuation of what he began in 1905, where he proposed his special theory of relativity, which described the behavior of light in a vacuum. Now, a consequence of Einstein's theory was that time and space were not absolutes, nor were they separate. They were, in fact, different expressions of the same fundamental reality. Another consequence of his theory was that matter and energy had equivalency, as is summarized by his famous equation E equals mc squared. And as we explored in a previous episode, the Relativity Revolution, Part 1, Einstein's theory effectively resolved the inconsistencies and tensions between the growing field of electromagnetism and how subatomic particles behaved, with Newton's theories of gravity and motion, which had been, up until this point, considered canon among scientists, to the point that the term Newtonian physics was interchangeable with classic physics. In any case, shortly after publishing his special theory of relativity, Einstein decided to expand upon it in order to account for gravity. And this was due to the fact that by this time in the early 20th century, Newtonian physics were coming into question. There were inconsistencies and anomalies in our universe that classical Newtonian physics simply couldn't account for. And as noted in the second installment in the Relativity Revolution, this included long-term changes in Mercury's orbit. In any case, Einstein began to rethink gravity by considering some of the main considerations that went into Newtonian gravity. For example, Newton described gravity as an instantaneous attraction between two point sources of mass, and Einstein began to question that. Special relativity had taught that nothing in the universe is instantaneous. Everything is bound by the speed of light. Nothing can reach or exceed it. And second, he factored in how gravity was indistinguishable from acceleration. And as special relativity taught, acceleration causes time dilation, where the observer who is accelerating and traveling at close to the speed of light will notice that their perception of time differs considerably from an observer that was at rest. And so from this, Einstein came up with a theory of gravitation that said that massive objects do not experience an instant attraction with other massive objects through gravitational attraction, but that gravity itself is a force that is exerted on space-time which causes its four-dimensional geometry to become curved, or rather alters the curvature of the geometry. And this means that objects which fall into this curvature, they will trace it, they will become influenced by it, and they will experience time dilation consistent with the level of acceleration. So, for example, if you're standing on planet Earth, you're experiencing a constant force of acceleration of 9.8 meters per second towards the center of the planet. If you were to jump from a plane, doing some skydiving, you would fall at a consistent rate of 9.8 meters per second per second. So you're accelerating by an additional 9.8 meters for every second that you're falling. Now, this theory went on to have immediate appeal and acclaim. It was validated in 1919 in the Arthur Eddington experiment, which observed the sun during a full solar eclipse and viewed a star that was at the time passing behind the sun, but it appeared to be adjacent to the sun because the gravitational force of the sun had altered the curvature of space-time around it, causing light to follow that curved path, making it appear as though the star were visible next to it. Now, general relativity, as it came to be known, it has been validated 9 ways from Sunday over and over and over again for about a century. And what's more, it predicted the existence of objects and phenomena in our universe before they were ever observed, not the least of which were black holes. Black holes had been theorized as a resolution to Einstein's field equations by the 1920s, 1930s, but scientists did not observe evidence of them, indirect evidence, until the 1950s and 60s. And this was confirmed by looking at objects in certain parts of space, how they behaved, how they were clearly being influenced by a very powerful gravitational force, which could not be seen. And from this, astronomers inferred the existence of black holes, and it wasn't until 2019 that we could actually obtain images of a black hole where we could resolve the bright disks of swirling gas and dust that surround them, and that was the Event Horizon Telescope getting a picture of M87, a supermassive black hole in the middle of a rather massive galaxy. In any case, 1950s and 1960s were also known as the golden age of general relativity because of all the tests and verifications that were going on that were now possible thanks to advanced telescopes. And one thing astronomers noticed when they were observing distant galaxies was that, like our own galaxy, these would rotate around a common center or galactic bulge, and that from the rotational curves, as they were called, or the speed at which they were rotating around that center, you could infer how much mass was in that galaxy. And when astronomers did the math, though, they came up short. They said that based on all the visible matter, that is to say the stars, the dust, the gas that's all swirling around the middle there, these galaxies should be rotating at this speed, but they're in fact rotating at a much different speed, which suggests that there's a lot more mass there than what we can see. And so this created a rather considerable conundrum. Scientists concluded that either general relativity is wrong, or it works differently in larger settings, larger scales, or there is mass there that we can't see. There's mass that is in our universe that makes up a considerable portion of all mass in it, but which does not interact with light the way normal matter does. Now, the possibility that general relativity was wrong seemed unfathomable because, as I said, all the experiments designed to test it in the most extreme conditions, even around black holes, they've all proven that general relativity is bang on, right on the money. So what could account for this discrepancy when viewing the universe on cosmological scales? Everything we've seen about space and the laws of astrophysics indicate that the laws are the same in all contexts, in all reference frames, so this gave credibility to the idea that there was, in fact, invisible mass out there. And this came to be known as dark matter. And from their calculations, astrophysicists have determined that dark matter makes up roughly 85% of mass in the universe. the remaining being so-called baryonic matter or luminous matter, the kind that we can see. However, the intrigue and the controversy didn't end there. Another thing that had been happening since Einstein's revolution in the 1920s, after general relativity had become accepted theory, scientists began to debate whether or not the universe was expanding or contracting or in a steady state. Now, Einstein was a big fan of the idea that the universe was static and unchanging over time, and he came up with a concept to rationalize that. According to Einstein's field equations for general relativity, the universe would have to be contracting. The force of gravity of all the mass, all the matter in the universe would be pulling everything closer and tighter together until eventually it'd go crunch. So the only way to explain why it wasn't doing that was to say that there was another force holding gravity back. And Einstein added this to his equations, and he called it the cosmological constant, as denoted by the Greek letter lambda. But as other theorists and critics pointed out, depending upon the value of the cosmological constant, the universe could also be expanding. This force which holds back gravity, if it were stronger than gravity, would be pushing the cosmos further and further apart. Now, Einstein rejected that idea. However, Einstein's theories and his preferences would go up against observational evidence soon enough. Throughout the 1920s, famed astronomer Edwin Hubble had been conducting observations from the Mount Wilson Observatory in California, and he had, among other astronomers, confirmed that what were thought to be nebula inside of our galaxy were in fact galaxies beyond the Milky Way. And this was because there are now telescopes with the necessary resolution to observe these nebulous collections of light that looked like dusty, bright patches, and to resolve individual stars within them. And that confirmed that these were, in fact, distant galaxies. But another thing that Hubble noticed by 1929 was, if you examined the light from these galaxies through a spectrometer, you would note that the light was being shifted either towards the red end of the spectrum, i.e. redshift, or to the blue end of the spectrum, blue shift. Now, the only way to explain this was that the wavelength of the light was either being stretched or compacted, because as Einstein demonstrated, the speed of light is always constant. So if the space between you and the light source is expanding, the light will not slow down or take longer to arrive, but its wavelength will be elongated. And based on his observations of redshift and blueshift, Edwin Hubble confirmed that, with the exception of the closest galaxies to our own, such as Andromeda, all the other galaxies were moving away. Einstein saw this in 1930, and he ditched the cosmological constant. He called it the greatest blunder of his career, and it was accepted. The universe is in a state of expansion. And so, throughout the 1930s, well on into the 1960s, this led to an ongoing debate about the true nature of the universe and how it all started, and it came down to two schools of thought. And on the one hand, you had proponents of the steady-state hypothesis who believed that the universe was particularly old and that new matter and new galaxies were being created all the time. On the other hand, you had proponents of what came to be known, jokingly, as the Big Bang theory. And this view was championed by physicists like Georges Lemaitre, who had also determined that the cosmos was expanding. And he and other theorists, they ventured that if the universe is in a state of expansion, and we know for a fact that it is, then if we wind the clocks backwards, then it must have occupied a much smaller volume in the distant past. And so they theorized that at one time, all matter in the universe was created in one hot instant in which the universe began to expand suddenly, and as it grew larger and further outwards, it cooled, giving rise to the first subatomic particles, then atoms, and then eventually all the building blocks needed for stars and planets and eventually life. And Lemaitre was criticized because there were many who felt that he was trying to slip his theology in there, given the fact that he was in fact a priest. as well as an astrophysicist. And so this debate would go on for decades. But one thing that the Big Bang hypothesis had going for it was a testable presumption. They said that if, in fact, all matter in the universe was created by a big, hot, blazing burst, then there would be leftover radiation from this event, relic radiation, if you will, and it would be visible at the most distant edge of the cosmos because, given how this radiation would be restricted to the speed of light, then its distance from our observation point would indicate the true age of the universe when the Big Bang happened and when cosmic expansion began. And by the 1960s, lo and behold, astronomers detected a pervasive background radiation in the microwave domain that was apparent in all directions that they looked and at the same intensity. And this came to be known as the cosmic microwave background. And what scientists quickly concluded was that, yes, this is in fact the relic radiation left over from the Big Bang. It has traveled through an expanding space since the beginning of time to reach us, hence why it's only visible in the microwave end of the spectrum, because it is so heavily redshifted that it is beyond any visible light, it's beyond the infrared, and by measuring that redshift, they were able to come up with an estimated distance of between 13 and 14 billion years. And ongoing refinements of these measurements have produced the current value, which is 13.8 billion years, plus or minus a couple eons. And so the debate was effectively settled. The universe was created in a Big Bang. All matter and energy originated from one single instant in space and time. And the universe has evolved ever since through expansion. And with Einstein's theory of relativity as sort of the cornerstone, this led to the emergence of Big Bang cosmology. And an integral part of this cosmology was the understanding that the universe would gradually decelerate over time, expansion would slow, and eventually contraction would begin. And so the universe, which began with a Big Bang, would end in a big crunch. However, by the 1990s, and with the deployment of the Hubble Space Telescope, scientists were about to get another shocking revelation. You see, prior to the Hubble mission, astronomers were restricted to looking back up to 4 billion years into the cosmic past. That was the limit of ground-based observations and ground-based telescopes due to atmospheric interference and the fact that light could not be resolved from objects more distant than roughly 4 billion light years. And this was one of the main reasons for Hubble's development. Dr. Nancy Grace Roman, who is a distinguished and illustrious figure, she was NASA's first chief astronomer, and one of the few women to actually work in astronomy and physics at NASA during the 1960s, she proposed how a space telescope operating in low Earth orbit would be free of any atmospheric distortion and interference, and could therefore take the clearest and most detailed pictures of the cosmos ever seen. And she lived to see her dream come true because in 1990, when she was 65, Hubble launched for orbit, and after an emergency realignment of one of its primary mirror lenses, it began returning the clearest and most detailed images of the cosmos ever seen. But what it also managed to do was allow astronomers to do deep fields, which meant that they could see galaxies in the distance up to 10 billion light years away, which means that they were able to study what most major galaxies looked like in our universe roughly 10 billion years ago. And what they noticed from all these deep field studies was that the universe was expanding at a different rate. In short, shortly after the Big Bang, there was a period of cosmic inflation or rapid expansion. This slowed temporarily as the major structures of the universe formed, the first stars and galaxies, but then expansion sped up again. And for the first 10 billion years of the universe, the rate of expansion seemed relatively consistent. But then, roughly 4 billion years ago, it began to speed up. And because astronomers were only able to see to the 4 billion year ago horizon, They believed that the expansion of the cosmos was what they'd been measuring. But looking farther back in time, they realized that, in fact, no, the rate of expansion is not slowing down, it's getting faster. And this once again completely threw them. And it raised Einstein's theory of a cosmological constant, which, as I said, back in the day, some speculated that depending upon the value of that constant, the universe could in fact be in a state of expansion. And more importantly, if the value was high enough, it would mean that over time, as the large structures of the universe got farther and farther apart, the force counteracting gravity would have more of an impact. And so, the farther apart that galaxy clusters and superclusters get from each other in the universe, the faster they're going to recede from each other. And so this upended the idea of a big crunch and created some rather frightening scenarios. Some astronomers argued that the universe would continue to expand until the last stars winked out of existence, and the cosmos would be permeated by black holes and complete darkness. This is known as the heat death scenario. Or that the universe would continue to expand until the fabric of space-time itself was ripped apart, known as the Big Rip. Either way, scientists needed a name for this mysterious cosmological force, which was not only holding back gravity, but was overpowering it. And so the term cosmological constant was resurrected, but the more popular nickname, dark energy, which was meant to coincide with dark matter, that's what really caught on. So by the 1990s, and ever since, cosmologists have been plagued by these two aspects of the cosmos, which together make up the dark universe. And the reason I say plagued is because, to date, the only evidence of their existence is indirect. We cannot see dark matter. We have been unable to isolate a dark matter particle. And dark energy is something that, while we can observe how it works, it is very difficult to measure, and attempts to do so have created what's known as the Hubble tension. And this refers to the fact that when employing different methods to measure distances in our universe, astronomers have come up with conflicting measurements. And to explain how that works, first we'd have to discuss what's known as the cosmic distance ladder. So basically, because we live in a relativistic universe that's subject to expansion, astronomers will use different methods to determine the relative distance of objects over larger and larger scales. Step one in the cosmic ladder is using stellar parallax to measure the distance to nearby stars, and that consists of taking two measurements from Earth when it is on opposite sides of the sun, and then comparing them to extrapolate the distance by comparing the angles at which the object is observed in the night sky. Step two consists of using a standard candle, which means using variable stars that vary in the amount of light that they emit, but also in their distance to us. And so astronomers will use changes in their relative luminosity to once again gauge their distance from us. And step three consists of using type 1 supernova. So what becomes of stars when they reach the end of their lives, they explode off their outer layers in a fiery burst. The extreme brightness that a supernova will generate will allow astronomers to make relative distance measurements for objects that are up to 1 billion light years away. So at this point, we're now getting far beyond the local universe. And step four is to use redshift measurements, which is what Hubble used to determine that all the galaxies in our vicinity, except for a token few, were moving away from us, thus proving that the universe was in a state of expansion. But at cosmological distances, and that consists of measuring redshift from very distant galaxies and from the cosmic microwave background itself. Now we're talking in excess of 13 billion light years away. In any case, when comparing the steps in the distance measurements for the local universe to those at cosmological distances, scientists noted a discrepancy. And while the James Webb Space Telescope, it was hoped, would help resolve this tension by making the most accurate and detailed observations of the early universe ever, It is really only added to the tension by noticing that during the early days of the universe, once again, there was a rate of expansion that can only be explained by the presence of other forces, which include a new theory known as early dark energy. So astronomers are really not able to resolve the mystery of dark energy yet, nor have we resolved dark matter. Nevertheless, all our observations to date have led to various theories being floated and ventured, and basically they all come down to one thing. Either general relativity, as we know it, is wrong when applied to cosmological scales, or there are, in fact, other physics and other matter there at work that we just can't quite detect. And to say that general relativity is wrong, there is an alternate theory known as modified Newtonian dynamics, or MOND, which says that beyond the edges of galaxies, the laws of gravity, instead of the gravitational pull becoming weaker due to distance from the massive objects, that gravity itself becomes a consistent force. And this has managed to simplify some of the calculations and explain some of the discrepancies, but it creates a whole new mess of problems in physics, so it has not yet been adopted as the prevailing theory. We still stick to the idea that relativity is sound and dark matter is real. And another reason why scientists are doing that today, why they maintain that our cosmological model still comes down to relativity and dark matter with dark energy, is because relativity has been tested so many times and in some of the most extreme environments, including supermassive black holes, and how they bend space-time around them, that there really doesn't seem to be any reason why it wouldn't apply over cosmological distances. And given the fact that there are phenomena in our universe, including black holes, which elude detection because they do not interact with light and normal matter via electromagnetic forces, which is to say black holes emit and radiate or absorb no light, because anything that is accreted onto their faces just disappears within the event horizon. What's more, scientists have become aware that there's a lot more mass in the universe than what we readily see because of light scattering and cosmic dust, which absorbs light and prevents a lot of matter in the universe from being seen in optical wavelengths. And so this has led to radio astronomy and infrared astronomy, X-ray, UV, and gamma ray astronomy, which has shown that, in fact, the universe is permeated by a lot of matter and energy that is not immediately accessible to our eyes. Because phenomena like that are known to exist on our universe, there's really no reason to suspect that there would not be a type of matter that also doesn't interact with visible or baryonic matter in that standard way. It interacts via gravity only. All the other forces of electromagnetism and weak and strong nuclear forces, not so much. And in the coming years, 2 missions will be dedicated to investigating these phenomenon. This includes the European Space Agency's Euclid telescope, which launched back in July, and the Nancy Grace Roman Space Telescope, which is scheduled to launch by 2027. And Euclid, named after the classical mathematician and one of the forefathers of geometry, it is going to be using its powerful optics to examine the universe up to distances of 10 billion light years, coupled with observations that lead right on up into the present. And from this, it's going to be investigating the geometry of the universe, specifically for the sake of measuring the influence of dark matter and how it has affected the expansion of the universe and the evolution of its large-scale structures. The Nancy Grace Roman telescope, meanwhile, aptly named after the mother of Hubble because it is, in every sense, a successor mission to Hubble, it's going to conduct the deepest field views ever obtained. It's going to be looking back all the way to 13 billion light years into the past. And among its many objectives, which include exoplanet hunting and collaborating with the James Webb Space Telescope to identify and designate objects for follow-up studies, it will be measuring the effect of dark energy over time. So testing just how rapidly the cosmos has been expanding at any given time in its evolution, And hopefully these missions lead, or at least contribute to, a resolution of this ongoing problem, resolving the Hubble tension, resolving the issue of where is all this mass that we don't see, is general relativity correct or not, and what is ultimately responsible for the expansion of the cosmos. Is it an unforeseen force or something else, some other exotic physics we don't know about? And if we can do that, then scientists will come away with the understanding that the predominantly held cosmological model, known as the lambda cold dark matter model, is in fact correct. It's just that some of the finer points, some of the necessary tweaks have eluded us up until this point. But regardless, it's a pretty good bet that these missions will raise additional questions as well as hopefully resolving some. And such is the nature of astronomy and cosmology. We're constantly learning about the universe in which we inhabit because not only is it so incredibly vast, it's very, very complex. The laws that govern it do appear to come down to size and scale. So every time we expand the field of our observations and stretch the limits of what we're able to study, the more we realize the universe is like one big gigantic onion, but we're peeling away at it from the inside out. With every new layer, it seems that there's additional considerations that have to be factored in and taken into account before you can even begin to understand how it all fits together. And that, ladies and gentlemen, is the dark universe, which accounts for two of the most pressing cosmological mysteries currently on our plate. It's comparable only to a grand unifying theory, a theory of everything, which tells us how the behavior of subatomic particles, which is described by the field of quantum physics, how that correlates to the behavior of large-scale structures, which is described by general relativity and gravity. How do the four fundamental forces of the universe, described by these two theories, all work together? We still don't know. But we're working on it, and that will be a subject for another episode. In the meantime, thank you for listening. I'm Matt Williams, and this has been Stories from Space.
We hope you enjoyed this episode of Stories from Space podcast with Matthe Williams. If you learned something new and this podcast made you think, then share itspmagazine.com with your friends, family, and colleagues. If you represent a company and wish to associate your brand with our conversations, sponsor one or more of our podcast channels. We hope you will come back for more stories and follow us on our journey. You can always find us at the intersection of technology, cybersecurity, and society.